on that goofy online mechanism that I was really more than anything else just experimenting with, please go ahead and pass them to the homework, the aisle that's closest to you, and I'll pick them up over the next few minutes. Online homework set. There was a question that you probably couldn't answer. And I don't know how people did it. Either by talking to people in the past, maybe it's explained better in the book than it was, but it was one of those things where I was teaching and I forgot that day to talk about it. And this was the business about jet streams that are zonal and jet streams that are meridional. And so I want to spend just a moment not dwelling too much on how you did it, and instead talking about what the answer is. So I'm going to switch over here to the projector for a second. There we go. And I want to just draw a picture here, and I want to illustrate what it means for jet streams to be zonal and jet streams to be meridional. In both cases, we're still talking about the jet streams. Whether we're talking about the polar jet stream or the subtropical jet stream, it's still a jet stream. It's still mostly going from west to east. But from day to day, the configuration of what that jet stream looks like changes quite a lot. So just to kind of give you a sense of scale here, let's put a Nebraska on here. If the jet stream is... I'm sorry, go ahead. Oh, wow. How did that happen? This way? Wrong or right? Yeah, that's better. Okay. Thank you for catching that. And now it's really small, too. Zoom. Where's Zoom? They give us, like, no cord for this thing. Close enough. We're only going to draw a couple things today. Alright, so there's our Nebraska. Just to give you a sense here, when the jet stream is zonal, what zonal means is it's just flowing more or less straight from west to east. A jet stream, the term that we use is that the jet stream is zonal. It's just flowing from west to east. We use that same word when we talk about like intertropical convergence zone. Yeah. If the jet stream is just going straight from west to east, we describe the jet stream as being zonal. If the jet stream is meridional, what we're going to see is that the jet stream is still mostly flowing from west to east, but it's doing so as it meanders to the north and to the south. So you get a jet stream that looks something like this when the jet stream is meridional. These are going to be powerful vocabulary words when we get back from spring break. I want to show you something on... So, okay, first off, a question that always happens is people ask why. Why does the jet stream do this? Why is it sometimes straight and why is it sometimes wiggly? And all I can tell you is that is a crazy complicated problem. Let me tell you by analogy what I'm talking about. Have you ever noticed, like if you have a cigarette, sometimes the smoke just rises in a nice little straight pencil-thin line off the edge of the cigarette, and other times it wiggles as if, there's all these little meanders as it moves? Have you ever noticed that sometimes when you run the water in the faucet, especially if you're just running it a little bit, it just flows, it almost looks like a tube of glass. It's just so perfect and smooth. And other times it's sort of splashing and spliggling as it goes down. Spliggling is a real word, write that down. As it goes down from the fall. Have you ever noticed that some rivers are really pretty straight and other ones meander all around? It's all a related problem. The business of why flow sometimes flows straight and sometimes flows in these meanders is a complex problem that it requires like 600 level math classes to explain, to have really any chance of doing. But you have seen examples of this in your real life, that the flow can do things like this, smoke or rivers or water or whatever. One thing to tell you, first of all, when you see a picture like this that shows the flow in the jet stream meandering, I know I was an atmospheric science major in this class many years ago, and I was confused by such a diagram, and I thought it meant like the jet stream got closer to the ground here and farther from the ground here. No, I mean as in it goes to the south, and then it makes a left turn and it starts headed to the north, and then it makes a right turn and it's headed to the north, to the south rather, okay? I don't mean down and I don't mean up. And that is a problem because we then make the whole situation vastly worse by giving names to these features. Names that make you think I mean down and up. See, here's the deal. This feature here where the jet stream was sort of going to the south and then made a left turn and headed to the north, that feature is called a trough. Troughs are drawn with a dashed line more or less down their middle. A trough is when the jet stream is curving down to the south and then makes a left turn and starts headed to the north. And with a name like trough, you would be forgiven for thinking that means that part is like the bottom of the trough. Like as in it's lower. Maybe I'm just thinking you'd be forgiven because I made that mistake. In the same sort of way, This feature where the jet stream is headed to the north and then makes a right turn and goes more towards the south is called a ridge. And we draw a ridge, we indicate a ridge on a map with a zigzaggy line more or less right through the middle of the ridge. Again, with a name like ridge, you'd be forgiven for thinking the thing is higher. It's not higher. Okay? It's just going off to the north and then turning back towards the south. Troughs and ridges are going to be huge. Troughs and ridges are going to be about the story that takes us most next, well, not next week, the week after that, to tell, which is the story of how cyclones and anticyclones are created. I always get asked, why were there areas of low pressure and areas of high pressure? If you had asked, I would just have to say, you'll have to wait. It takes us a long time. But troughs and ridges are a big part of the story. You're going to get patterns of cyclones and anticyclones when you have troughs and ridges in the jet stream. Another beautiful example of one of the amazing things about the atmosphere, troughs and ridges are up there in the up at the jet stream. They're up near the top of the tropopause. Cyclones and anticyclones are at the surface. You're going to see how troughs and ridges in the jet stream cause cyclones and anticyclones down at the surface, especially cyclones. We're not going to dwell too much on anticyclones in that part of the lecture. Wow. So I have no idea how you got that question right, if you got the question right or whatever on the homework set for today. Was that question 2 or something like that? It said, what did it mean if the jet was... Now, maybe in the new printing of the book I missed it. There was a lovely description. Maybe you had people who had class in the past where a very similar question was asked on the homework set. I don't know. To some extent, I don't really care. However, you got the right answer. If you had the mental exercise and gave the right answer on there, that's great. I will probably, if I do the grading of these, I'll probably make that question extra credit or something, just because I meant to tell you about this the other day. I ran out of time, and then I forgot to come back to it when we keep the next day class on Wednesday. Anyway, all right. So we'll be coming back. I'm going to put a little star by that material. That's going to be coming back when we get to back from spring break. All right. Cool. All right. When last we left, we've been talking about air masses. And we have been talking about the fact that air masses were like parts of the subtropical high or parts of the polar high that are broken off. Everywhere right now. This class is going to eventually be on YouTube because I decided I was like being way too kind to people. And somebody's going to Google it and they're going to find this and they're going to say, no, they're not parts of it. Wait till you see the comments on Dr. Shruggy's YouTube lectures. No, air masses are not exactly parts of the polar high and parts of the subtropical high that break off, but that's a really good way to think about them. Okay? But we're going to see a better description later. But either way, think of it as like, you know, here's this nice, big, warm area of the world called the subtropics, and there are high-pressure systems there, the subtropical highs, and you can think of it as part of them bulging northward towards the poles, warm air moving to the north. And at some point, it encounters the polar front, where it is meeting at the surface cold air coming from the polar highs. These are colder air masses. They are generally going to be either cold and moist or cold and dry. MP and CT. No, CP, continental polar. The ones coming from the south will either be like maritime tropical, if they're coming from someplace like the Gulf of Mexico, or continental tropical, if they're coming from like Arizona and New Mexico and places like that, where it might be hot and dry. But no matter what, at some place they came across that boundary, which we call the polar front. That will be the place where they meet. Air masses have this boundary between them, and that boundary is going to be called a front. Notice how we've so far been calling it the polar front. The polar front just sort of means this boundary. Notice how it kind of drapes all the way around the world at about 40, 45 degrees north, something like that. And it is that boundary with cold air on one side, the warm air on the other. And from place to place, and from time to time, one air mass will be pushing the other ones out of the way. The cold air masses might be pushing the warm air masses out of the way, so that polar front advances farther to the south in that area. And in other places, maybe the warm air is pushing the cold air out of the way. We're not yet worried about why these air masses are moving. Have faith. But if the warm air masses are pushing the cold air masses out of the way, that polar front will be a warm front. Let's have a definition. Let's talk about what a front is. There. Fronts. Fronts are boundaries at the surface. Well, let's say boundaries. Let's not worry about where they are just a second yet. Between air masses that have different densities. I don't know that you would have come up with exactly that definition, but after looking at things that had a polar front involved, my guess is you would have guessed the word boundary was in there. You probably would have understood there were air masses, one on one side, one on the other, and that they had different, and then you probably would have put temperature. And of course, in the ideal gas law, temperature is a powerful way to change the density, right? I mean, if both of these two air masses have about the same pressure, they're high pressure systems, let's say 1,020 millibars in each of them, something like that. Then by changing the temperature, you change the density, right? The air mass that is warmer is less dense. The air mass that is colder is more dense. It turns out, though, that's not the only way to change the density of two air masses, to change the density. You can also change the density by talking about how much water vapor is in the air. Now, I have tried over the years many different ways to teach about this way in which humidity changes the density of air. And the best thing I ever did, when I put it together, I then, as a PowerPoint, I then did it as a narrated PowerPoint, and it's off on YouTube or something like that. I am not going to, because it was like, hey, I did it right. I did it right for ones that got it. Okay? So I then put it up there. So I will give you guys that PowerPoint / YouTube, whatever it is exactly, and you'll watch it. It's like 5 minutes long, but it has the right explanation. But we'll do that after spring break, because if I give it to you now, yeah, that's going to happen. Okay. So for now, though, just this business that there are different densities, for most of the kind of fronts that we're going to be talking about, when we talk about different types of fronts today, it's really the temperature that's different between the air mass on one side of the front and the air mass on the other. Okay? But moisture could be the story, too. So fronts are going to be the boundary between air masses at different densities. This is a very old term in meteorology. This is a very old term in meteorology because it comes from a very old term in military science. In military science, they use the word front to talk about like the boundary where armies are meeting. Okay? In fact, much of the notation that we get about fronts in meteorology, you already know because you TiVo the Weather Channel. You know we're going to be drawing these lines with the little, triangles on them. Those triangles are called teeth. How awesome is that? You would be surprised to find out possibly that that's actually the notation that like military scientists and military studies people use to show like when the French were invading up the Rhine River, that they show the position of the leading edge of the front, all using those same symbols. Because that's how early meteorologists, I'm not talking about like cave meteorologists, I'm talking about like 100 years ago, that was how they were envisioning this. Like, the cold air and the warm air, where the cold air was surging forward like a front on a military, and that was the way we were picturing it. That's like they were invading each other. Okay? It's a stupid term, but it's kind of a cool term. Now I'm going to go ahead and tell you that we're going to have 5 types of fronts. I don't think we're going to hit all 5 types of fronts today, but we're going to tell you in advance that there's going to be 5 types of fronts. There's going to be cold fronts, and warm fronts, and stationary fronts, all of which you, somewhere along the way, probably hit those words. Either reading in the book slipped up, Dr. Shrugged slipped up, you're watching the Weather Channel, whatever you're doing, you're reading somebody's weather blog. Please don't read somebody's weather blog, that's just tragic. Whatever, you've heard those terms. What you probably haven't heard is occluded front, and you probably haven't heard of dry line. Now, not all of these fronts are examples of the polar front. The polar front, remember that term from a couple days ago, the polar front is where cold air from the north is meeting warm air from the south. The difference between the two air masses is their temperature. That's why they are dense on one side, cold and dense on one side, warm and not dense on the other side. Okay? In fact, only these first 3 are examples of the polar front. Spell polar front. When we learn important things about the polar front, like the thermal wind relationship, what we're talking about is things that can happen along the cold fronts, the warm fronts, and the stationary fronts. What happens with the thermal wind relationship? Oh yeah, that meant that when you had a polar front at the surface, sitting right above it was the mid-latitude jet, aka the polar jet, aka the jet. Right? So that can happen on cold fronts, warm fronts, and stationary fronts. We'll be drawing pictures of all of these and stuff like that in just a little bit. Occluded front fronts are different. They're not going to be about the difference on either side of the front being about differences of temperature. They're both sides of the front will be cold, but they'll have differences in density. Occluded fronts are not terribly exciting in terms of what kind of weather is happening, and they are a key step in how cyclones work. That's where we're really headed with this. By sometime after spring break, we're going to be telling the story of how troughs and ridges lead to the formation of cyclones and how cyclones go through their life cycle from formation to moving air masses around to dissipation. It's going to be a lovely story. It's the birds and the bees of meteorology. What gives birth to these cyclones? Cyclogenesis. And what causes them to die? That's going to be included principle for that story. We're not going to worry about them until then. Because we don't exactly have a ton of cool weather around. Dry lines are a really cool story. Dry lines are a type of front where the two air masses on either side are the same temperature, but they have differences in density because one side is dry and one side is moist. And they are going to be the story about, like, Tornado Alley. Okay? That part of the country, like in Texas and Oklahoma and Kansas and so on, where tornadoes happen, especially in the spring, is going to see a lot of dry lines. And these guys are going to be great for making tornadoes. Okay? We're not going to get that far today, probably. That'll be like on Monday. So let's start talking about these fronts. And we're going to start by talking about cold fronts. Now I have to, hey, where am I getting all these pictures that I've been showing you up here on the projector? From the full outline of each unit. Right? I send out, there's an announcement in blue line 2. You can follow this little outline. You can see, oh, I see, now we're in this section, now we're in this section. And one of the things that's there is all the pictures that the textbook company provides us on its CD when we choose their book or whatever. And I'm going to show you an example here of a cold front. Here is a cold front. A cold front is this sort of three-dimensional shape. It's this three-dimensional boundary between a cold air mass and a warm air mass over here. And in the case of a cold front, the cold air is it's a polar front down here at the surface. It is where cold air from the north is pushing and moving warm air from the south out of the way. Okay, we're not yet worried about why the air masses are doing this. We will learn later why air masses are on the north. Okay? First thing first. Look how this is sort of a three-dimensional shape. Okay? It's kind of like the blade of a snow. See, remember I told you air masses have a shape? Cold air masses, kind of think of them when they're behind a cold front like this. I like to think of them as being thick and heavy, kind of like pancakes batter or pancake syrup or something like that. When you pour it on the plate and it spreads out, it kind of has that little leading lip. You know, this is like the leading edge of the pancake batter or pancake syrup or whatever works for you. It's kind of a leading edge. And this leading edge right here is fairly sharp. How deep is this thing? Just to give you a sense here, this is a few kilometers deep. It's at the surface and extends upward a few kilometers, but the polar jet as well is higher than this. These air masses are a surface thing, because that's where they picked up their properties. This became a cold air mass by hanging out, stagnating, over Siberia or Canada or something like that, right? One thing everybody likes to know about fronts is how they're drawn. Fronts are drawn as a line on the map that shows where the frontal boundary is at the surface. You know why? Because it's really hard to draw this thing in 3 dimensions. Okay? So the line here shows you where the front is at the surface. In the case of a cold front, we normally draw it as a blue line with blue triangles along it, pointing the way the cold air is trying to go. Those blue triangles are called teeth. I love that phrase. And there's no significance to where the teeth are. You know what I'm saying? If you want to draw more teeth, you want to draw fewer teeth. Where the teeth are doesn't matter. Okay? It's just there to show you that's where the cold air is advancing. This leading edge here, where the cold air is pushing warm air out of the way, picture a snowplow. That cold air is dense and heavy. The warm air is relatively light. The cold air has no trouble pushing that warm air out of the way. And so when that cold air pushes that warm air out of the way, this leading edge here is pretty steep, and it just is hurling that warm air out of the way. Rising motion. Rising motion. Along a little narrow area right there by the cold front itself. See how all the rising motion was on a really narrow area right through here? You see it at warm fronts later, it's different. Relatively steep rising motion right here as this cold air plows the warm air out of the way. I used to have a big sheet of poster board for this, and then some other teacher saw my demonstration and called it a puppet, and I threw it away, and now I wish I had my puppet. Here's my cold cold air mass, my front. Cold air is under here. Warm air is over here. The cold air mass has no trouble pushing that warm air mass out of the way. As a consequence, cold fronts move pretty damn fast. Cold fronts are the fastest moving of the fronts we're going to see here. How fast is fast? 30, maybe 40 miles per hour. They move pretty fast. They're pretty steep. They are, the area though, I mean, when you have steep rising motion, right there on that steep leading edge of the cold front, you don't get rising motion over a very large area. Later, when we see other types of fronts that are more gently sloped, they have their rising motion over a broader area. Well, you're going to get your clouds of precipitation then in a fairly narrow, heavy band with a cold front. So on this side, on the warm side of the cold front, you're in a warm, moist air. You're a warm air mass, probably moist, although who knows? Could be continental, tropical, or something. Probably the winds are out of the south, something like that. And then cold front comes through. Holy cow! Now you're in this cold air mass. Winds are probably from the north or northwest or northeast, something like that. You're probably moving into an area of precipitation. Yeah. You know what? It actually works pretty well if we then do talk about this by comparing them right away to warm fronts. I would like to kick the butt of the person who put this picture together for the textbook, because they did a stupid thing. They reversed which side was north. Right? Remember before on the figure, this side was cold and this side was warm? Why did they do this? This annoys me. Alright, so you have to be able to think about the fact, now this is the cold side. Here's a cold air mass. Here is a warm air mass. The boundary between them is a warm front. Warm fronts are drawn as a red line with semicircular, half-circular teeth. We still call them teeth, even though I just had to see it with that muppet teeth. The half-circular teeth pointing the way the warm air is advancing. Now, warm air is not very good at kicking cold air out of the way. Warm air is pretty light stuff compared to the cold air, which is dense. Instead of being a sharp leading air mass, leading edge of that front, where that front is, warm air is plowing that cold air out of the way, think of it more as sort of gently leaning against the cold air and saying, come on, move, move. Okay, it's not really moving very well at all. Warm fronts move slow. What's slow? 5, maybe 10 miles per hour. They don't move very fast at all. I bet you don't have trouble guessing how stationary fronts move. Telling the difference between a stationary front and a warm front can be a real change, okay? A real pain in the butt. They're even more similar than you're going to realize. But for now, warm fronts, they move slow. 5, maybe 10 miles per hour. Not great. And that warm air is trying to push that cold air out of the way. But mostly it's just sliding up on top of it. The whole warm air mass, instead of pushing that cold air out of the way, is mostly just sort of sloping up that warm front in 3D. The colder, denser cold air, let me start that sentence over. The colder, denser cold air is underneath the frontal boundary, and the warmer air is mostly just sliding, gliding right over the top of it. And it is a very gentle slope over a large area. See how gentle that slope is compared to the slopes on cold front? Now I'm going to tell you something. That slope is ridiculously too steep. In a real warm front, that slope is about 500 to 1. So like for every inch I went up, I'd have to move my front 500 inches this way. I mean, I can't even draw a line that close to flat. Real warm fronts are ridiculously flat. The warm air mass is mostly just sort of gliding over the top of the cold air rather. The warm air is sliding. Oh, I'm not going to use words like sliding and gliding. I'm going to use the right word. Overrunning. Overrunning. The warm air is overrunning the cold air along a warm front. I'll give you that word spelled out and everything for you. Overrunning. The warm air is overrunning the cold air mass along the warm front. Yeah, it's also slightly pushing. Actually, the warm air is not really pushing the cold air out of the way. It's actually a matter of the same forces that are at work that makes the warm air mass move is also making the cold air mass retreat. Okay, who cares? I care. That's overrunning. Good vocabulary word to know. Look at all that overrunning happening along that up ahead of the warm front. Look at where the weather is happening. The warm front is here at the surface. All that lifting and all that cloud production and precipitation happens over a broad area. And notice that the farther ahead of the warm front you are, the higher higher those clouds are. I mean, if you're out over here and you look up, you probably have clear skies, you're in some cold air mass. All right? The front's getting, I can't move the projector, so I'm moving me. Okay? We're driving towards the front here. I'm still in the cold air mass. I look up, hey, some cirrus clouds. I look up, oh my goodness, some altostratus clouds. They're getting lower. Hey, nimbostratus, it's raining on me. Hey, now I'm in the warm air mass. All the weather is poleward of the warm front. Big, gentle area of precipitation and clouds way out ahead of it. 500–600 miles ahead of the warm front. You have this broad area of rising motion. Very different from a cold front, which had a relatively narrow area of precipitation along it. Now I'm going to blow your mind. Our textbook doesn't actually say this, but plenty do. In many ways, cold fronts and warm fronts are the same damn thing. Doesn't it sound like by their name they'd be the opposite? But in many ways, they're the same thing. Allow me to show it here. Here's my puppet again. This is the frontal boundary in 3 dimensions. Cold air down here, warm air over here. That's north, that's south. Sometimes I actually bring like little signs that say north, south, but that again seems a little too puppety. Okay. Cold front. They don't make sound. Cold front, pushing its way down this way. This is a great choice of lunch to have on YouTube. Warm front, gentler, but still sloped so that the cold air is underneath it and the warm air is under it, and this way. I mean, really, only the difference is the slope and which way it's moving. But it's still just a boundary between cold air on one side, warm air on the other side. Cold air underneath, warm air, I don't have a third hand, so I have to go underneath, and warm air up on top of it. I should have kept my puppets. They're the same damn thing. And they're both polar fronts. Because both of them, here, I'll put a cold front right here, have that polar jet sitting up on top of it. Okay. Now I'm going to go ahead and just annoy you further. Stationary front. A stationary front is another polar front. And this time, neither the cold air mass nor the warm air mass is advancing. Now, the story is not so simple about the slope of stationary fronts. Some stationary fronts are very steep, some of them are very shallow. It's a whole complicated bit of... the name just scared out of me. There's an equation that determines how steep the frontal boundary is. Archimedes equation, I think. Whatever. Doesn't matter. Don't worry about the slope of a stationary front. Stationary fronts are pretty darn close to stationary, though. They're not going to be moving. And that might make them sound like they don't really do much or they're not important in meteorology, but quite to the contrary. Actually, they are still places where cold air and warm air are meeting. They're just not pushing each other out of the way. So like if this is my stationary front hanging here, maybe warm air is encountering the stationary front and riding up it. And that's rising motion and producing clouds and precipitation. And guess what? It ain't moving. So like flooding situations are often associated with stationary fronts because the weather's not going. I mean, it's not going anywhere. It's going to be raining in the same place. That is not the only way. Don't write down the only way floods happen is because of stationary fronts. No, but like they can be important in that sense. Stationary fronts are also polar fronts. What does a stationary front look like on a map? For whatever reason, the textbook doesn't give us, okay, so we had blue line with blue triangular teeth pointing the way that cold air is moving for a cold front. We had a warm line, a red line with red semicircular teeth pointing the way the warm air is moving for a warm front. How do you draw a stationary front? Well, let's do that real quick. Stationary front. A stationary front is drawn as a line with blue triangles on one side of the line and red semicircles on the opposite side of the line. Again, where you put the triangles and the semicircles doesn't matter. It isn't like there's significance to those spots. They are just, notation. They're just telling you that this is a stationary front. By the way, this business of cold front, warm front, stationary front being one blue, one's red, one's got blue and red, you'll notice you could actually draw them in black and they look just fine, right? I mean, the color's helpful, but you can tell the difference between a tooth that is a triangle and a tooth that is a semicircle just fine, especially when it's not just Dr. Troggy scribbling and full of caffeine. Okay? So, I mean, atmospheric science students buy pencils? Yeah, they do. But, I mean, in general, you could do this in black and it would be just fine. Where do I want to go with this? tell you one thing and then tell you the other part on Monday, or I can tell you thing 2 and tell you the other part on Monday. I'm going to tell you the other thing. All these different types of fronts are associated with cyclones. Fronts are a big part of the story about how cyclones work. Now, what we're going to be learning about here is how fronts are associated with cyclones. Because cyclones have a life cycle. They start. How do they start? They start off as an area of low pressure. It gets lower and lower until it's worth caring about. It's a cyclone, and it has rotational winds around it. And then in this life cycle, the cold fronts and the warm fronts are going to be moving. The cyclone will have cold fronts and warm fronts. And then at some point, the cyclone will die. It will experience cyclolysis. Lysis is a suffix that means something like death of. They have a life cycle. We're anthropomorphizing a bit here, right? But they have a life cycle. Cyclones last something like 5 to 10 days. They go from a bouncing baby cyclone to one that old and dead meteorologists don't care about it in about 5 to 10 days. And we aren't going to worry about their life cycle per se until Monday, but what I want to show you is how fronts are associated with that. If I have a cyclone, it's an area of low pressure on the map. Again, let me put Nebraska on there for scale. Yeah, that's great, Nebraska. Cyclones, as you will recall, have counterclockwise rotation in the northern hemisphere. Which means on their west side, they have winds from the north. They are pulling cold air from the north down towards the south. Which means somewhere on the west side, someplace, there will be a cold front, where we experience the boundary between cold air to the north and warm air to the south. Similarly, on the east side of your cyclone, the winds are from the south, which means warm air from the south is pushing its way north. And that means that someplace along the way here, and I'm drawing kind of a strange looking one, but that's the right thing, we're going to have a warm front, where we are experiencing the boundary between the warm air from the south and the retreating cold air from the north. So like in this example here, maybe this air mass north of the cold front, maybe this is, I don't know, continental polar. Here's some cold air being dragged to the south by the cyclone. And ahead of the warm front, you've got some warm air that was coming off, someplace way far down to the south here, you've got a subtropical high. And you've got some warm air being pulled up here, maybe this is maritime tropical. And that warm air on the east side of the cyclone is being drawn up along this warm front, and the warm front is pushing its way slowly north, and this will be your, maybe continental polar air on that side again. But look at the pattern here. Cyclones have cold fronts and warm fronts. The cyclone occurs along the cold front and the warm front. In fact, remember that warm front and that cold front, they were part of the polar front. The polar front being that boundary that in fact kind of snaked its way all the way around the world, at all the longitudes, all the way around the world. All the way around the world, there will be these places where the polar front bows to the south and it's a cold front, and places where the polar front bows to the north and it's a warm front. And along the way, there's these cyclones along the way. They're kind of like riding the polar front. Like picture cars on a roller coaster. Okay? They have whole families of cyclones that are scooting along the polar front at any given time. It's so anthropomorphized. We get these cyclones that are scooting along the polar front. And as they move along the polar front, on their west side, they're dragging cold air south. This is fundamentally why those air masses were in motion. The air masses are just being dragged around by the cyclone. The cyclone's doing the work. And on the east side of the cyclone, warm air is being dragged towards the pole. That's why that warm air mass is moving. It's not because it's doing something. The warm air mass isn't what's doing the work. The cyclone's doing the work. Why is the cyclone doing the work? Well, that's that whole forces thing that we did in the last unit, right? Pressure gradient force, Coriolis force. As it's rotating, it's by definition dragging cold air to the south on the west side and warm air to the north on the east side. So you're always going to have fronts associated with your cyclones. And usually you're going to have the cold air on the cold front rather on the west side, and some kind of warm front on the east side. And so your cyclones can look like a lot of different images. You can have cyclones, for example, that look like. Alright, here's another cyclone. Maybe this one, the cold air has pushed way far to the south already. These are terrible markers. Okay? Here's a lovely cyclone. Okay? Cold air behind the cold front, warm air ahead of the warm front, cold air ahead of the warm front. Beautiful. It's like maybe this is continental polar, maybe this is continental tropical, and maybe this is maritime polar up here. You've got cold air masses on the poleward side of the fronts. You've got warm air masses in the, I'll just go give you the name for this feature, so there's no secrets between us. The area between the cold front and the warm front as part of a cyclone is called the warm sector. Where the warm air mass is. The warm sector, man, I love that vocabulary word. Sector, like a piece of the pie. Remember, that cyclone is a center of low pressure. If you drew some isobars on here, they look something like this, right? And as the winds are going around that cyclone, they're dragging that cold air down to the north, all the way down here, warm air up this way, etc. So cyclones always have kind of that look. They always have an area of low pressure with a warm front to the east and a cold front to the west. I always think they look a little bit like legs. Okay? You got a cold front and you got a warm front, and they should look kind of like the leg, like they're kicking or something like that. Okay? You'll see lots of pictures of this unit with the readings and stuff like that, and there's tons of them in the textbook. Okay? It's a cyclone. The world will have lots of these going on at any given time. All the way around the world, all along the polar front, you'll have a family of cyclones. I'm going to try to draw something that has a family of cyclones on it. For example, here's a cold front with a low pressure system, and maybe there's a warm front coming off of it, like this way, and then maybe that actually becomes a stationary front for a while, before becoming the cold front of the next cyclone. Okay, and then maybe here's the next warm front. See how they make kind of like a series of this could just, I could keep drawing this draped all the way around the globe. Why did I push off the edge again? Sorry. See how I could just keep drawing that? Wouldn't that be graceful? Wouldn't that be lovely? All the way around the world, we have this polar front with a big old polar high off to the north, subtropical highs down here over the south. As these cyclones are rotating, they're dragging cold air to the south or pushing warm air to the north, and oh my goodness. Meanwhile, up above all this, there'd be jet streams, right? The mid-latitude jet streams hanging out above here by the thermal wind relationship. In this case, probably going in the form of troughs and ridges, right? Because, I mean, you can see how the jet stream's going to have to stay above all this. Oh my. Oh my. But that cold front is moving faster than that warm front. Remember? Cold fronts move pretty fast. Cold front, warm fronts barely move at all. Which means at some point, those cold fronts are catching up with the warm fronts. Uh-oh. At some point, that cold front starts catching up with the warm front. That's going to be called an occluded front. We're going to put that off till 9. I have no way starting talking about occluded fronts with 10 minutes left on the Friday before spring break. Okay? Boy, I'm going to tell you a little bit about dry lines. Dry lines are another type of front. Dry lines are fronts that separate two different air masses, but instead of having different, they're a front, so they have to separate two different air masses with different densities, but now instead of the difference being the temperature, this time dry lines will be separating air masses that have different humidities. There is no standard meteorological symbol for a dry line. I have no idea why. But we tend to draw them in meteorology as either brown or red lines, with just sort of scallops along them like this. I think it's supposed to look like clouds of dust. So like here's Nebraska just for scale here. Okay? And this is your dry line. Now, I didn't just choose this place by random to show you where to draw in, because actually, from Nebraska south to like, Kansas and Oklahoma and Texas is a really good place to get dry lines. Because on one side of the dry line, we have continental tropical air masses, hot and dry. They're coming off places like Arizona, northern Mexico, etc. Meanwhile, off to the east of the dry line, you have maritime tropical air masses coming off the Gulf of Mexico. Right, if I just try here, not very well at all to scale. There we go. Just the Gulf of Mexico. Gulf. Florida, okay? Great. Not at all very well done. Okay. You can see though where like air coming off the deserts of Arizona and New Mexico and so on would be hot and dry, and air coming like up off the Gulf of Mexico would be could be very warm, but is also moist. And so this boundary between the warm, moist air and the warm, dry air may have no temperature difference at all, but might have a very large density difference because one's so much moister than the other. Now, the question is, which one is more moist? This is that PowerPoint that I told you about, or I think we made it as a narrated PowerPoint on YouTube, whatever it is. Here's the deal. That PowerPoint will explain to you why this is, but for now, that it is important. The dry air is dense. The moist air is light. Oh my gosh. If you had to have guessed whether dry air was heavy or whether moist air was heavy, you probably would have guessed the moist air is heavy. You would have been wrong. That's okay. Graduate students in meteorology get that wrong all the time too. That's what that little PowerPoint's about, is I finally one time figure out how to explain it right. The dry air is heavy and dense, the moist air is light. So as that front between the dry air on the west and the moist air on the east goes along, this heavy, dense air has no trouble lifting and plowing this moist air out of its way. Rising moist air. Does that sound like a good way to make a thunderstorm? Yes, it does. And in fact, it happens to be a particularly good way to make tornadic thunderstorms. Which is why this band here that separates in the United States, where we just happen to have good geography, that we have a nice hot and dry place right next to a hot moist place that makes nice examples, especially in the spring of dry lines, we get tornadoes in Tornado Alley. And as you'll see in the fourth unit of the course, we have more tornadoes than the rest of the world put together by like 10 times. Okay. This is a great setup for dry lines, and dry lines are a great setup for tornadoes. Alright, I think that's enough for a Friday before spring break. We will talk about the life cycle of cyclones, which will include the story of the sneaky occluded fronts next time, which is Monday after spring break, and then we do put it all together with cyclogenesis. How did all this stuff get started? Why are there cyclones? Have a good and safe spring break. This would be good.
Explain it well.